Hi everybody. Today we're going to be working on exponents and radicals. This is a competency for ninth grade math. We're going to start with a review of exponents and then we're going to move into radicals. At the very beginning, let's have a do now. So as you can see, this do now has to do with space. You just got a call from a group of scientists trying to determine the distance between Earth and the Sun. Using your special telescope, you are able to determine that the distance from the Earth to the Sun is 150 billion meters. The scientists are so happy and want you to write an essay about your discovery. After writing 150 billion meters several times, your hands are tired from typing. Is there a faster way to write this? Pause the video, write down an idea that you have, and then we will check it in a minute. Are you ready to move on? The answer has to do with exponents. So exponents are just a quicker way of writing a really long line of numbers. So for example, if we need to multiply 2 times 2 times 2, we can write that a shorter way. 2 arrow 3. Now that's not how we actually say it. We say 2 to the third. That little arrow means that the 3 is up there. That means that we're taking 2 and we're multiplying it by itself 3 times. The 2 is the base. The 3 is an exponent. So the answer is still 8. 2 times 2 times 2 is 8. 2 to the third is also 8. It's the same thing. So how do we use exponents in real life? Well, going back to our space example, 150 billion meters is a long number to write. We can instead write it as 1.5 times 10 to the 11th meters. What that means is 1.5 times 10 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 times 10. So you may have noticed by this time that using exponents is really just a shorter way of showing repeated multiplication. In this case, I took all the 10s and I just repeated multiplying them 11 times. That's where the 11 exponent comes from. Here are a couple quick problems to practice. Number 1, what is 4 to the first? Number 2, what is 1 to the fifth? And number 3, what do you notice about the difference between 4 to the third and 4 to the second as compared to 4 times 3 and 4 times 2? Pause the video, answer the 3 questions, and start again when you are ready. Are you ready? Here we go. Number 1, what is 4 to the first? The answer is 4. We're taking 4 and we're multiplying 4 to itself 1 time. So 4 to itself is 4, the end. Number 2, what is 1 to the fifth? Well, that's 1 times 1 times 1 times 1 times 1. The answer is 1. Number 3, what do you notice about the difference between 4 to the third and 4 to the second as compared to 4 times 3 and 4 times 2? Well, the difference is in how many times we're multiplying something. Okay, 4 times 3 is 12. 4 to the third is 4 times 4 times 4. That's 4 times 4, which is 16, times 4. Ooh, that's a really big number, okay? 4 to the second is 4 times 4, which is 8. 4 times 2 is also 8. So in that case, that's the same. But 4 to the third is definitely different from 4 times 3. It's a much bigger number because we have more 4s that are getting multiplied. This is called exponential growth. It's increasing very, very quickly. What are some examples of things in life that grow exponentially, meaning they build very quickly in size due to multiple repeats? Pause the video and think for a minute. What types of things in life increase that fast when you're multiplying a number times itself many, many, many times? Did you think of an answer? Here are a couple. Some examples of exponential growth include the growth of populations, infections, and technology. So here's a graph that's something relevant for right now, the number of deaths of coronavirus in the United States. As you can see on February 29th, at the bottom of the graph, there weren't many. But then on March 7th, it increased. And then March 14th, it increased. And by March 25th, we have this huge number. Look how fast it increased in just a short number of days. This is called exponential increase. Okay? Once a few people have coronavirus, if they cough and somebody else gets it, well, then more people. And then all those people cough and then even more people get it. And then all those people cough and even more people get it. That's how things are increasing so quickly and exponentially. Okay, let's move into some rules of certain operations when you're dealing with exponents. So for example, what happens when you have to multiply exponents? Well, number 1, they have to have the same base. So looking at our example with number 2 here, you'll see we have a to the second times a to the third. The answer is a to the fifth. Well, how did we get that? Normally, when we see a multiplication, we're used to seeing the numbers involved multiplied, but not with exponents. If we have a to the second, that's a times a. And if we have a to the third, that's a times a times a. So how many a's are multiplied all together? 5 a's. So the answer is a to the fifth. Now, if you notice, a to the second times a to the third, if we take those exponents and we add them, 2 plus 3 is 5. So, in conclusion, when multiplying exponents of the same base, keep the same base and just add those exponents together. New situation, taking the power. 5 to the second all to the third. Pay attention to those parentheses. That means the whole thing is to the third, not just a part of it. When you have a base and an exponent inside parentheses with another exponent on the outside, multiply those exponents. So 5 to the second, all raised to the third, means 2 times 3, which is 6. So we keep the same base. Now it's 5 to the sixth. What is 5 to the sixth? Well, it's 5 times 5 times 5 times 5 times 5 times 5, which is 15,625. Dividing. If we're going to divide exponents, again, we need the same base. Okay, so in this little example here, on the top, we have the same base of x. X to the m divided by x to the n equals x to the m minus n. So what's happening here? We're just subtracting the exponents. So for example, 4 to the fifth divided by 4 to the second, well, 4 to the fifth is 4 times 4 times 4 times 4 times 4, and 4 to the second is 4 times 4. Well, those 4s on the top and the bottom of the fraction, they cancel each other out. How many 4s are you left with? You're left with 3 4s on the top. So 4 to the third is the answer. But how could we also get that? We just subtract those exponents. The fifth minus the second, 5 minus 2 is 3. When you have two exponents with the same base, subtract the exponents. Here, we can't really do anything because we don't have the same base. Y and x, that's not the same base, so this is actually done. There's not much we can do there. Here we do have the same base. 10 to the ninth divided by 10 to the fourth. The answer is 10 to the fifth, 9 minus 4. Similarly, here we have x. X is a base. 12 minus 8 is 4, so the answer would be x to the fourth. The zero rule. 2 to the fourth divided by 2 to the fourth equals 2 to the 0. What happens when you have an exponent with a 0? Where does that 0 come from? How does that happen? Well, remember the rules for dividing. How can you get a 0 exponent? Well, 2 to the fourth divided by 2 to the fourth. Remember, you subtract exponents when you're dividing, right? 4 minus 4 is what? 0. That's where that 0 comes from. It's those two exponents that are being subtracted from each other. So if 2 to the fourth divided by 2 to the fourth is the same thing as 2 to the 0, what happens when you divide something by itself? Well, the answer is 1. 1 divided by 1 is 1. 5 divided by 5 is 1. 10 divided by 10 is 1. James divided by James is 1. So that means that 2 to the 0 is 1. So any base raised to the power of 0 just becomes 1. Okay, last one, negative exponents. 5 to the negative 2. What do you do with that? Well, you move the exponent to the other side of the fraction. So right now it's in the numerator. We're going to flip it and we're going to put it in the denominator. So 5 to the minus second becomes 1 over 5 to the second, which is the same as 1/25, 1 over 25. 4x to the minus 2 equals 4 over x to the second. We just put that x on the bottom. I can't put the 4 on the bottom because then it's not a 4 anymore. It would be a 1 over a 4, which is a 1/4. That's not accurate. Lastly, we have x to the negative third and y to the negative seventh. Well, we have to put them on the other side of the fraction, right? So the y thing goes to the top, the x thing goes to the bottom. That's how that answer happens. All right, to summarize everything, if you've got to multiply exponents, you add them. If you've got to divide exponents, you subtract them. You've got to raise something to the 0 power, the answer is always going to be 1. If you've got an exponent for an exponent inside parentheses, multiply them. You got negative exponents, flip to the other side of the fraction. Perhaps you might want to take a moment and pause the video and write down this summary. Okay, are you ready to move on? Here is a big practice problem. You are definitely going to want to write this down. Okay, it is a division. Look at the division sign in the middle. This first chunk, negative 2, m to the fourth, n to the negative seventh, p to the seventh, m to the eighth, n to the negative 2, that's all one group in one big parenthesis, divided by negative 2, m to the eighth, n to the seventh, p to the fourth, all raised to the second power. Woo, remember one of those rules? Write this down, try it out. It uses all the rules we talked about. We'll go over it when you're ready. Are you ready? Okay, here we go. This is the answer and the process to get the answer. Pay attention to all the exponents. What is one of the first things that you do? Well, we got to deal with the parentheses on the bottom and the denominator of the fraction. So everything is raised to the second power. What do you do when you raise it to the second power? You multiply. So negative 2 to the second, m to the 8th times 2 becomes m to the 16, n to the 7th becomes to the second power, becomes n to the 14th, and then p to the 4th times 2 becomes p to the 8th. On the top, in the numerator, we've combined all of our negative n's into n minus 9 to the negative 9th. Then what happens? Well, we have to divide our fractions. Remember when you divide our exponents, when we divide, remember, you are subtracting, okay? So that's how we're getting m to the negative 4 and p to the negative 1 and n to the negative 23. Now what do we do with all these negative exponents? Well, we can't leave them in the top. Remember, you have to put them to the other side of the fraction. So we're going to put them in the denominator. So the answer becomes 1 over 2 m to the fourth, n to the 23rd, and then just p. Let's move on over into radicals, and Connor is going to give us our lecture about that.
Alrighty, thank you, James, for discussing exponents and the various properties. Now we are going to flip to radicals. Okay, so radicals are a very common operation that you will see in algebra and the advanced mathematical courses beyond algebra. So radical. So radical dude is actually a colloquial phrase in some slang English circles where you may hear radical refers to something being very, very awesome. Okay, so do not confuse the mathematical radical with the very awesome radical that you might hear in pop culture references. All right, here we go. So the radical. So this sign that you see at the top, which looks kind of like a squiggly line, but actually has the property of being the inverse of the exponent. So when we think about the exponent, we're normally thinking about expanding a number. So we talk about 2 squared, right? 2 squared is going to be 2 times 2, right? We know 2 cubed is going to be 2 times 2 times 2. Well, with the radical, we're basically unwinding or undoing the action of the exponent. So the other name that the radical has is the root. And so the square root is the most common, and that is what you will see as the normal radical sign, which I'm circling around right now. And so what this means is that if you look to the right here, if I were to take a number like 512, and I'm going to try to find the root of 512, well, what I can do is I can find what number multiplied by itself a certain number of times is going to give me that value. So if I'm taking the root of 512, and let's say I'm taking it to the 1, 2, 3, 4, 5, 6, 7, 8, I'm taking the 8th root of 512, my 8th root would be 2, because 2 times itself 8 times is going to give me 512. And so for the second root, we'll normally call it the square root. The reason why we do that is because originally roots were used to find what the sides of a square would be if we know the area. So for example, if the area of a square is 16, then the square root would be 4, because one side of the square would be 4, the other side of the square would be 4, and then the area of the square would be 16. And so the same terminology extends to the cubed root. And so if we do the cubed root of some value, let's say 64, right, then again our cubed root of 64 is going to be 4. Because if I have 64 cubic centimeters as the size of my cube, then that is going to mean that each side is going to be 4 centimeters long. All right, so now we're going to look at how it's written. So the radical is commonly written as the denominator of an exponent. So for example, the cubed root of a, right? The cubed root of a can also be written as a to the 1 over 3 power. All right, so this is a little bit different than how you normally might think of fractions. But just like James showed with the negative as an exponent, the negative doesn't mean the negative number, but what it refers to is we're using the negative as a way to denote 1 divided by some base to the exponent power. So we're doing the same thing where we're using the fraction to denote what a radical is going to represent. All right, so now we're looking at the parts of the radical. So we have some different terminology for everything involved with this operation. So whatever we're taking the root of, whatever we're taking, putting the radical sign over, that is going to be known as the radicand, right? The radicand. And so if I'm taking the square root of 49, right? 49 is my radicand. In this case, I'm taking the cubed root of 7. And so 7 is my radicand. And so we learned coefficient from the last video. And so a coefficient is really any number which is being multiplied by another part of a term. And so in this case, our one term is going to be 5 times the cubed root of 7. It's one thing that we can conduct an operation against. And so in this case, 5 is our coefficient. And finally, index is going to be the value that we're taking the root of. So I could be taking the 4th root, I could be taking the 5th root, I could be taking the 6th or the 7th. And so our index is going to be the value of the root. And finally, the radical is just the name of this symbol. All right. Now we're going to look at some radical properties. And so radical properties are really the same as exponent properties. So addition and subtraction is going to be conducted the same. So if I say the square root of c plus the square root of c, then I am going to get 2 times the square root of c. Now the same thing goes with subtraction. If I say the square root of c minus the square root of c, then I'm going to get 0, because that's essentially with a imaginary coefficient of 1 times the square root of c minus 1 times the square root of c is going to give me 0 times the square root of c. And 0 times any number or any quantity is going to be 0. All right, and then so multiplication and division, just like with exponents, we're going to combine. If I have the square root of 2, for example, times the square root of 2, I can actually combine 2 and 2 to each other, and it will be turned into the square root of 4. Finally, with exponentiation, if I take the square root of 3, and then I also say I want to take the square root of 3, then I'm going to do the same thing I would do with exponents, where I'm multiplying those exponents to each other. But in this situation, we're going to turn them into fractions. We're going to turn them into fraction exponents. So in that situation, it would be 3 to the 1 over 2 power, and then it would be parentheses to the 1 over 2 power, and then it would be in total 3 to the 1 over 4 power, which rewritten would be 3 to the fourth root of 3. Finally, with negatives, we're going to do the same thing we do with exponents. We're going to say if 1 to the negative 1 over 2 is going to be 1 divided by the square root of 1. All right, and then finally, just the square root of 0, or the cube root of 0, or the fourth root of 0 is just going to be 0. And we're not going to take the 0th root of anything because that's not possible, right? We can't take a non-root, right? That actually would be an undefined answer. All right, now finally we got.
All right, okay, pause the video now and practice by attempting these 4
we
problems.
can look at it originally as d to the fraction 1 over 3 power. And so if we had d to the fraction 1 over 3, we know that should be turned into a radical, which would just be the cubed root of d. But because we have this negative sign, we need to turn it into 1 divided by the cubed root of d. And so that's going to be our solution. All right, now let's jump down to the next one. And so for this one, you need to combine like terms here. So if we don't want to bring it into decimal, we don't want it to get messy, we want to simplify this as best as we can. And so we're going to combine these like terms, the 3, our coefficient, times the cube root of 3, plus our invisible 1 coefficient times the cube root of 3. We can add those coefficients, which would give us 4 times the cube root of 3, plus our unlike term, 2 times the cube root of 5. All right, now for our next one, we've got the multiplication property that we can apply here. So we've got the square root of g times the square root of 4g, and so we can just multiply what's inside and then try to take the root. So we've got the square root of 4g squared. We can take the square root of 4. We can take the square root of g squared, giving us 2g. Finally, we've got the cube root of 8, and this should really be the cube root of 8, rooting or taking the root of also the square root of h. So it's a root inside of a root. And so this is a multiplication. If you saw it as multiplication, that's okay. But for this one, we're gonna look at it as a radical inside a radical. So pause the video and try to redo this if you thought of it a different way. All right, so for this one, obviously the cubed root of 8 is going to be 2. And then what's going to happen when we take the root inside of a root, it's going to be the same thing as an exponent inside exponent times an exponent to the power of an exponent. We're going to multiply the two together. So it's going to be 2 times the 6th root of h, because the square root should be represented here, times the cube root would be the 6th root of h. All right, and so that is really it for today. We'll have some more practice problems on the Google Classroom. Please remember that this is a competency. You need this to successfully move on to 10th grade math. And if you have any questions, do not hesitate to shout out. Thank you again for tuning in, and we'll see you next time.